Assalamu alaikum everyone. So today we will be talking about satellite communications and we will be having lecture number 26. So these are the topics which we will be covering in this lecture. First of all, we will try to establish that why we need satellite communication. Then when we talk about the satellite communication, so we use uplink and downlink. So we will try to justify that why we are using uplink and downlink for satellite communication. So in case of satellite communications, there are different types of satellites on the basis of different characteristics. So we will be talking about the classification of those satellites on those different characteristics. And satellites can cover some area, so they actually offer some coverage area. So that coverage area establish the footprint of the underlying satellite. So we'll be talking about the satellite footprint, and there are different frequency bands which are allocated to satellite communication. So we will be talking about the frequency ranges and different bands in case of satellite communication. So as mentioned, we use uplink and downlink, but there is another point that we use different frequencies for uplink and downlink. So we will be talking about why we use different frequencies for uplink and downlink. Propagation delay. So we will talk about the signal propagation delay, and one of the important element of satellite is transponder. So we will be talking about the design context of the transponder, and there are certain environmental and weather conditions that can affect the satellite communication. So we will be talking about the effect of rain on satellite communication. So as satellite communication is in satellite communication we use microwave frequencies. So why we use microwave frequencies for satellite communication? Then there are different system elements regarding the satellite design. So we'll be talking about the those different system elements regarding the satellite design. And then losses. So of course we come across different losses, so we'll be talking about those different losses that we have to face. And finally we whenever we attempt to enhance the capacity allocation, so we need to adopt certain strategies. So we will be talking about those different methods for capacity allocation and enhancement. So here we will try to find out that why we need satellite communication. So as we know that the shape of the earth is spherical, right? And we also know that we are going to use microwave frequencies in order to have the long distance communication, right? So if we talk about the microwave communication, so they travel in straight line. But for example, if I need to connect two stations, base stations, or maybe two communication points from one Atlantic to another Atlantic, right? So you can see that there is no straight line that I can draw in order to have communication. This is because of the curvature of the earth, right? So let me draw. If I want to have, so I need to build a tower to an enormous height. So this height, it can be in thousands of kilometers, maybe 1,000, 2,000 and more. So then I will be able to have, so I have to mount an antenna over here, and on this side I have to mount another antenna, then I will be able to have communication. But you can imagine the cost. first of all, it's very ridiculous to build such an antenna with such an enormous height, and then you can see if there is some problem, right? So you have to have huge amount of resources in order to repair, right? So there are certain elements, certain cost factors, certain technical elements that are involved that we cannot do that, right? So that's why we are interested in satellite communication. So we will be trying to justify that how we can overcome those different problems. And you can see that if even in that case I need a lot of repeaters, so I cannot, if I talk about this point, so maybe at this point I need maybe to build a tower, maybe half of the length. If here we have 1000 kilometer and tower, so here might be 500 kilometer. So even then it's enormous if we talk about the tower. So here you can see the graphical representation for our motivation to use satellite communication. So you can see we want to establish transatlantic link between two between points. So here in one part of the earth, and this is another part of the earth, so you can see transatlantic link. So you can see that how much height we have to achieve in order to have straight line microwave communication. So it's 750 kilometers, which is again on the higher side. So what a communication satellite is, it can be looked upon a large microwave repeater, okay, and it contains it may contain several transponders, and which that transponders, they actually listen to some portion of spectrum. So some portion is allocated for listening, amplifies it, and then broadcast it to another frequency to avoid interference with incoming signals. So it receives signals from the base station on the earth, maybe some satellite, other satellite in the space, and then it amplifies it and then broadcasts it to maybe some other satellite, and or you can say it can broadcast onto the earth after amplification. But remember here that we will be using one frequency for reception and other frequency for broadcasting. So this we will be talking about in more details after some slides. So actually, if I have to define a satellite precisely, so it's a repeater that receives signals from earth at one frequency, amplify it, so it is receiving signal from the earth and at one frequency, and then it will amplify it and transmit it back to the earth at another frequency. So remember, we are using two different frequencies that we have to take into account after some slides. So here we have the Earth station. So there are two Earth stations in a simple satellite communication link. One transmits the signal to satellite called transmitting Earth station. The other receives signal from satellite called receiving Earth station. So here we will be talking about the uplink and downlink. The communication link from transmitting Earth station to satellite is called uplink. So you can see this is the uplink from Earth station to the satellite, and here we have the downlink from the satellite to the receiving Earth station. So this is the transmitter. So our objective of course is to transmit the data from this point to this point. So you can see this is the uplink. So we will send data to the satellite, and satellite will receive this data on one frequency, that is the uplink, and then it will amplify it. So maybe if there are some there is some noise, so it can also remove noise, and then it will broadcast this by using the downlink, and we are using another frequency for the downlink, and in this way our objective is achieved, that is to transmit data from this point to this point. And you can see that in order to avoid this curvature, so due to this curvature of the Earth, we are not able to transmit the data directly from this point to this point, so we have to use the satellite. So we can attain different altitudes of orbits above the Earth when we talk about the satellite. So on the basis of those different altitudes and orbits, so there are three, we can classify three common types of satellites based on altitude, right? So that is GEO, MEO, and LEO. So here is the table: orbit, altitude, and then mission that we can accomplish by using those different types of satellites. So low Earth orbit, that is LEO, and it can attain an altitude of 250 to 1500 kilometer, and the possible missions we can accomplish, we can have Earth observation, right, meteorology, telecommunications, constellations. And then MEO, medium Earth orbit, and it can attain an altitude of 10,000 to 30,000 kilometer, so we can have telecommunications, constellations, positioning, science. Then we have GEO, geostationary Earth orbit, and it can attain an altitude of 35,786 kilometer. So here are the possibilities: telecommunication, positioning, and science. So elliptical orbit, so we have the altitude between 800 and 27,000 kilometer, and we can accomplish telecommunications. Then hyperbolic orbit, up to several million kilometers, so we use for planetary missions, right? Okay, so here we have more details of different types of orbits. Inclination over the equatorial plane, right? So equatorial orbits above Earth's equator, polar orbits pass over both poles, I is equal to 90 degrees, so here we have 0 degree. Other orbits called inclined orbits, so here we have I is between, it should be greater than 0 degree and less than 90 degree. So we have shown it graphically. So based on eccentricity, circular with center at Earth's center, and then elliptical with one foci at Earth's center. So here we have another configuration of different type of one of the type of the satellite orbit. So here we have established different types of satellites satellite networks on the basis of the altitude. So you can see it's almost the same, but we have VSAT over here, which we were not, right? So very small aperture satellite, so it is actually used. So the missions accomplished missions normally are private vans. So again, orbits. So here we have shown satellite orbits graphically. So you can see this is LEO, low Earth orbit, in yellow, and then in blue we have medium MEO, and in red we have geosynchronous orbit, right? So sometimes in literature you can find geostationary or maybe geosynchronous. So here we have mentioned geostationary geo, and here you can see we have geosynchronous orbit, right? So you can see the orbit type, height and period. So here we have one more extra bit of information, that is period. So if we talk about the LEO orbit type, it can attain this height, and the period is 1.6 to 1.8 hours, the time it takes to complete one period. And then MEO, it approximately takes 6 hours, and then GEO, it approximately take 24 hours to complete one period. So you can see that GEO is at the maximum height when we talk about the orbit. So here we have more details regarding geostationary orbit. Equatorial plane orbit period is 23 hours 56 minutes, so it's 24 hours. That's why we have approximately here, because of 56 minutes 4.091 seconds. So one sidereal day, this satellite appears to be stationary over any point in equator, because the reason is that Earth rotates at same speed as satellite rotates. So radius of orbit r is equal to orbital height plus radius of the Earth. So you can calculate the radius of the orbit where the satellite is moving around, and then average radius of Earth, we all know that it's 6378.14 kilometer. So if we talk about the geostationary orbit, so 3 satellites can cover the Earth, right? So because they are separated by 120 degree. So if I go back, so you can see for geostationary, so we can use this for positioning, for example global positioning system, and that's why we need 3 satellites in order to use the triangularization in order to calculate the position. So here we have non-geostationary orbit and GSO. So the orbit should avoid Van Allen radiation belts, region of charged particles that can cause damage to satellites, right? So, and this is the region we should avoid, around or roughly between 2000 to 4000 kilometer and between 13,000 to 25,000 kilometer. So we should avoid. And then we have LEO. So here we have shown graphically LEO, in inclined orbit with less than 1400 kilometer altitude. So in that case, satellite travels across sky from horizon to horizon in 5 to 15 minutes. So it needs handoff. Earth stations must track satellite or have omnidirectional antennas. Large constellation of satellite is needed for continuous communication. Complex architectures, so require tracking at ground station. So here we have HEO, highly elliptical orbit. So you can see the HEO I is equal to 63.4 degree, and HEOs are suitable to provide coverage at high latitude, including North Pole. Depending upon selected orbit, 2 or 3 satellites are sufficient for continuous time coverage of the surface area. So we need 2 or 3 satellites if we are targeting a certain coverage area. All traffic must be periodically transferred from setting satellite to the rising satellite, right? So here we have to transfer the traffic periodically from the satellite that is disappearing to the satellite that is appearing. So this is setting, disappearing, and rising. This is appearing satellite. So here you can see the configuration of the satellite orbit. So you can see we have a lot of satellites that are actually in LEO, 46%, and then if we talk about MEO, 6%, and again GEO, it's on second number. LEO is on the higher side or highest. Second number GEO, 43%. MEO, that is third, and then we have other 3%. So here you can see, if we talk about the physics, so why these satellites, they remain in their orbits. So this is the gravitational force of the Earth, and this is the inertial configuration force that try to throw away the satellite from the orbit. So this is balanced by this gravitational force. So as a result, we if we give very little thrust to the satellite, so it can attain the required velocity depending upon the push we actually are giving to the satellite. Okay, so here we will try to define the orbital period, the time taken by a satellite to complete one rotation in its orbit is called its period. So if we talk about, so if we start from here and we say that this is the orbit, so the time taken by the satellite to complete one rotation in its orbit is called its period. Takes 23 hours, 56 minutes and 4.1 seconds, so it's the same, and this is why it appears to be stationary by the observer on the Earth, moving with the same speed. Because when we talk about geosatellites, so they and the Earth, they move with the same speed. So it seems that it appears that this is a stationary satellite if an observer is observing on the Earth. So here we have satellite system. This is the height and this is the velocity that it can attain, right? So this is the additional parameter we are having, satellite geo, orbital height, and here is the velocity, orbital velocity. So you can see 3.0747, and this is the orbital period, the time taken to complete one rotation, right? So here if we talk about MEO, so you can see the velocity is increasing 4.8954, and the orbital height is decreasing, right? So we are actually approaching close to the Earth. So LEO 7.1272, so velocity is rising and the orbital height is decreasing. So we have noticed that as the altitude decreases, the velocity must be increased to minimize the gravitational effect. Because if I go back, so if I have to move here, so of course the gravitational force will be on the higher side, and in order to overcome this gravitational force, I have to raise the speed of this satellite, so that this rise in speed will increase the inertial centrifugal force, right? So in that way we can keep the balance, right? So here we will be talking about the footprint of the satellite, or you can say the coverage area of the satellite. So you can see the Earth's surface covered by satellite radiations is called footprint. Coverage area is inversely proportional to the frequency. Footprint will be larger if the frequency of the downlink is low. So if I go back and try to show you the uplink and the downlink. Okay, so So, and I will show you again. The coverage area is inversely proportional to frequency. The footprint will be large if the frequency of downlink is low. Okay, so you can have the relationship. So here we have tried to show the coverage area or the footprint for geosatellite. So that's why we need 3 satellites in order to calculate the position on the Earth, or you can say in order to use the GPS, global positioning system, or you can say we use triangularization in order to calculate the position. Here 1/3 of Earth's surface, so Earth is divided into 3 regions, right? So you can see first region, second region, and on the other side we have the third region. So AOR, Atlantic Ocean region, then POR, Pacific Ocean region, and then IOR, Indian Ocean region. So we have. So now we will be showing frequencies for satellite communication. So you can see we actually dedicate different letters or assign different letters to different bands, and then we have the frequency range, and then after that in the last column we have the use. So here we have L band, and the frequency range is 1 to 2 gigahertz, and this band is actually being used for satellite phones in order to have GPS, global positioning system. And then we have S band, and this band have frequency range between 2 to 4 gigahertz, and it is being used for satellite phones. C band, 4 to 8 gigahertz, it is used for TV transmission. Then X band, and then we have KU band. So these are very popular, C, KU, and Q band, right? So for KU band, the frequency range is between 12 to 18 gigahertz, and this is being used for TV transmission and communication. And then we have KA band, frequency range is between 26.5 to 40 gigahertz, and it is being used for internet data or satellite data communication. We have Q band and U band, they are being used for experimental purposes. So here we have shown that the bands which are being used mostly with their downlink and uplink frequencies, as mentioned, that whenever we are using satellite communication, so we use one frequency for downlink and another frequency for uplink. So for C band, so you can see that the downlink frequency is between 3700 to 4200 megahertz, and for uplink we have 5925 to 6425 megahertz, and for KU band we have 11.7 to 12.2 gigahertz for downlink, and for uplink we have allocated 14.0 to 14.5 gigahertz. For KA band, 17.7 to 21.2 gigahertz for downlink, and for uplink we will be using 27.5 to 31.0 gigahertz. So C band is the band that is being used mostly, and KA and KU bands are reserved exclusively for satellite communication, but they can be affected by the rain attenuation. So over here we will be talking about signal propagation delay. So as we know that the electromagnetic waves, they travel with the velocity of light, and that velocity of light is 3 into 10 to the power 8 meter per second. And if I use the formula S is equal to Vt, where T is the time, and I have to find out the time, so that is S over V. So here you can see S is the distance, that is altitude, and V is the velocity or speed. So if I have to define the uplink delay, or you can say the propagation delay from ground station to the satellite, so that is called, or that is named as uplink delay, and I will define this, the time taken from Earth station to satellite. And if I multiply this uplink delay with 4, so I will be getting round trip delay, right? So here we have the table, orbit, LEO, MEO, and GEO, and then average altitude. So here we have calculated the average altitude, uplink delay, and then finally we are calculating round trip delay. So you can see for LEO, average altitude 800 kilometer, and we have an uplink delay of 2.7 ms millisecond, and if we multiply this with 4, we will get 10.8 millisecond. So for MEO, you can see the altitude is 10,355 kilometer. Of course, we will be having more delay, uplink delay, 34.5 millisecond, and if we calculate the round trip delay, that comes out to be 138 millisecond. And for GEO, this is the average altitude, 35,786 kilometer, and you can see the uplink delay is on the higher side because we have average altitude on the higher side. So of course we have to multiply this with 4, and for 80 millisecond, or we can also say that it's almost equal to half a second. Okay, so here we have tried to show the round trip delay of GEO signal. So you can see that this is 0.25 from ground station to the satellite. So again from ground station to satellite. So if I need to calculate the round trip time, right? So you can see I have to multiply this for 4, 2, and 2. Okay. So this is an important component or element of the satellite. The bandwidth of the satellite is actually divided into channels, allowing many a station to use this bandwidth. The electronics that has to support each channel is called the transponder. Each transponder, it consists of a, so now we are talking about the circuitry of the transponder. We have a band pass filter to select a particular channel. Then we have to use the down converter, and then after the down conversion we will be amplifying, right, the output. We need output amplifier. So each satellite can have a large number of active and spare transponders, typically 12 to 44 active transponders in each satellite is usually. So if we want to calculate, we want to know the bandwidth of the transponder, 36, 54 or 72 megahertz, right? So here is the block diagram of a transponder, low noise amplifier, 6 gigahertz uplink antenna, and here we have the band pass filter, down conversion, local oscillator, right, and then we will be performing the down conversion. And here we have 4 gigahertz band pass filter, 4 gigahertz low power amplifier. So here we have HPA, high power amplifier, 4 gigahertz. So this is for downlink and this is for uplink. So this is the block diagram of a transponder. Then here we will be talking about the effect of rain on satellite communication. So rain, they actually can heavily affect the wireless communication above 10 gigahertz. So if we talk about the KU band and KA band, that actually operate above 10 gigahertz affected by rain, and especially above 20 gigahertz. So as mentioned earlier, that we will be using two different frequencies for uplink and downlink. So moreover, we will be using high frequency for uplink and low frequency for downlink. So we have to justify why we are doing so. So as we know, if we have a high frequency, so the beam of frequency will be narrow. So when we talk about the communication from ground station to the satellite, so the ground station, you can see from the ground station we have to focus or target the signal to a small point that is satellite in space, right? So it does it by using narrow beam produced by high frequency. So whenever we talk about the satellite from the space, so it has, we wish or we desire that it should be able to cover as much area as large as it can. So from the satellite point of view, we're talking about from satellite to the area on the Earth. So we want that it should cover larger area, or it should have a larger footprint. So in order to have that, what we need to do, we are actually using low frequencies, right? So that's we are using lower frequencies, that is actually representing F down, right? So here is so it does it by using broad beam produced by lower frequency, right? So we need to broaden the beam, right? And we can accomplish that by using lower frequencies. So moreover, as we know that the rain can affect high frequencies more than the lower frequencies, so they need to be boosted up more to overcome the propagation loss. The energy can be given to signal much more easily on Earth. So this is another reason that we have more resources on the Earth as opposed to the satellite that is actually at large distance, or that is actually having few resources within the space. So we can give more energy because we have more resources at the Earth. So that's why we are using the uplink frequency, that is from ground station to the space or to the satellite on the higher side, and the other frequency that is for the downlink or F down is on the lower side. So here we have shown up and down frequencies for C band. So you can see this is the uplink frequency, and that is from ground station to the satellite, and uplink 6 gigahertz, and this is on the higher side. And if we talk about the downlink frequency, so you can see that is from satellite to the ground station, so that is on the lower side 4 gigahertz. So if we talk about the satellite signals, baseband signals can be analog or digital, but the final signal transmitted towards the satellite or from the satellite is always analog, as it is an RF signal. So if we are talking about, if we talk about the baseband signals, so they can be analog or digital, but whenever we talk about the transmission or the ultimate transmission of the data from satellite to Earth or from Earth to satellite, so it has to be analog as it is in RF signal. So here we have shown different mechanisms in order to increase bandwidth of satellite, because this is our desire that we want to enhance the bandwidth of satellite. So there are different techniques. For example, we can use multiplexing. So we will be talking about those techniques in more details after some slides. And then we could also use audio and video compression in telephony and TV signals. And we can also have frequency reuse technique, same frequency but orthogonal polarization, and then increasing angular spacing of two satellites in same orbit using similar frequencies. So here we have the lifespan of a satellite. It has two life: design life and maneuver life. So life of the electronic system working in satellite. So this is the design life, and it is the life during which full maneuver capabilities exist in satellite to change its position on the fuel tank, storage capacity, and it is usually less than design life. So it is raised to the graveyard orbit, so where it is actually end of life. It is considered as the end of life. So here are different uses of satellites. So we can use the satellite for military purposes, and we can also use satellite for telecommunication, and then there are satellite phones we have nowadays, for example Thuraya. Then we have VSAT, very small aperture terminal, cable TV, digital broadband satellite with dish antenna. We can also have a global positioning system, and we need 3 satellites in order to calculate the position exactly and correctly. Then we can also have satellite internet, weather forecasting, and then of course if we want to have aerial view of some area, or there is some problem, some emergency situation, for example earthquake or maybe flood, so we can have the aerial view of the area by using satellite communication. Then GIS, geographical information system, X-ray and infrared view of universe, navigation, of course the aeroplanes and the other sea vessels, they can use the navigation technique by using satellites. And then we have some other applications of satellites. So here we have mentioned satellite missions. So you can see that most of these satellite missions, they are actually based on communication. And then we have 7% navigation, and then we have 6% military surveillance, and then again 6% some other that lie in some other categories if we talk about the missions. And then we have some other, for example 5% earth observation, remote sensing, then astrophysics, space physics 5%, and earth science 5%, right? Okay, so here we will try to justify that why do microwaves are used for satellite communication, why we need microwave in order to have satellite communication. So if we talk about the microwave communication, so they have high frequency to carry the information, long enough wavelength to penetrate the atmosphere. They do not rapidly disperse in atmosphere, so the power does not need to be very high to reach a distant point. So they can be focused by a suitable dish to increase the reception of low power signals. They can be modulated to carry signal and are resistance to interference. They travel in straight enough to be able to aim a certain focused point, line of sight. They are easy to produce and easy to detect. So these are the reasons that why we are using, and those all points, they are in the favor of satellite communication in their configuration. So here we have shown different satellite elements. If we talk about the space segment, so we have a satellite, right, and this is the ground station, and this is the coverage region, right? So ground segment, so you can see earth stations, right? So here we have the coverage region, right? So we will talk about in detail space segment, satellite launching phase, transfer orbit phase, deployment, operations. So the operations can be tracking, telemetry, and command station. SSC, satellite control center. OCC, operation control center. SCF, satellite control facility. And then finally we have to push it into the graveyard orbit where it has to retire. Then if we talk about the ground segment, collection of facilities, users and applications. So you can see here we have fixed ground station, and here we have the mobile ground station, right? So it's MSS, mobile satellite service, and FSS, fixed satellite service. Right, so this is almost the same, downlink, right, uplink. So here we have mentioned some more points that why two frequencies for uplink and downlink. So we actually mentioned more reasons, right? So first, we can also say that in order to avoid interference, we are using one frequency for uplink and another frequency for downlink. So if our system it can send a signal, then wait. The receiver could be protected from the transmitted signal on the same frequency, but with high speed continuous transmission, the receiver cannot be turned off while the transmitter is transmitting. So we cannot achieve that when we are receiving, we should turn off the transmitter part. So this is not the case whenever we talk about the high-speed communication, right? So an example of something that transmits and receives on the same frequency is pulsed radar, where the transmitter sends out pulse and then the echo is picked up by the receiver. Then we have another point. Signals have to cross the atmosphere, which presents a great deal of attenuation. So if we talk about the traversal of the signals from ground station to the satellite, so it has to cross the atmosphere. The higher the frequency, the more is the signal loss and more power is needed for reliable transmission. So if we talk about the ground station, so on the ground station we have capability to generate more powerful signal. When we talk about the satellite station, so it has very limited resources, so we should not expect to generate high power signals from the satellite because it has limited resources, and with those resources, so the lifespan of the satellite can be reduced significantly, right? So if we talk about the if we try to find the analogy of uplink, downlink for satellite communication and the mobile communication. So if we look at the mobile, so it also have some resource limitation. For example, we have limited computational power, we have limited battery life, we have limited display, right? So mobile is a portable device which cannot afford high power transmission. So of course limited resources, battery, limited power, the free space loss comes to play. The higher the transmitter frequency, the higher is the loss, since the mobile station, cell phone cannot afford to transmit at higher power to compensate for this loss, right? So that's why it must transmit on a low frequency as opposed to base station, that is the uplink. So here you can see if we talk about so this is base station, so downlink is on 935.20 megahertz, and this is the uplink. So you can see that the downlink is on the higher side and uplink is on the lower sides, right? So this is opposite to that of satellite communications. If we talk about the uplink, so for uplink we have higher frequency, and for downlink we have the lower frequency. But in case of cellular communication or mobile communications, you can see this tower or this base station, right? It has more resources as opposed to the mobile phone or cell phone, which has limited resources regarding battery time, regarding power, display, and computation. So you can see that the downlink is frequency is on the higher side, and uplink frequency, because here mobile station has to send data by using this uplink to this base station, so it's on the lower side. So here we have shown satellite transmission links. A station communicate by sending signal to the satellite on uplink, downlink. Downlink makes it attractive for services such as the distribution of TV program. So here we have shown direct to user services, right? So in this, on left hand side of your screen, so you can see one-way communication. We have broadcast. This is uplink. This is the base station, so the satellite will receive the data, and then it will broadcast to the rest of the targets onto the Earth. And here we have two-way services, right? So we can have uplink and downlink, repeater 2 and repeater 1 satellite. So you can see that we have here we have two-way communication, here we have one-way communication. So here are some of the satellite uses, satellite signals used to transmit signals and data over long distances for weather forecasting, for television broadcasting, and for internet communication and global positioning systems. So here we have mentioned advantages of the satellite. So here we have disadvantages of satellite: large upfront capital costs, space segment, and launch. So the cost is on the higher side. Terrestrial break-even distance expanding, interference and propagation delay, congestion of frequencies and orbits. So when we should use, or when we should go for satellite communication makes it attractive when the costs are lower than terrestrial routing. So when we don't have some other choice, so we should go for the satellite communication. So here we have some of the examples: communication to ships and aircrafts, and then we can use TV service, satellite communication for TV services, data services where we don't have any other data services, overload traffic, delay terrestrial investment. Okay. So here when to use terrestrial, PSTN, land mobile personal communication, right? So here we have frequency band allocation to FSS, fixed service satellite. Bands are allocated to different services at World Radio Communication Conference, right? Allocations are set out on Article S5 of ITU, International Telecommunication Union Radio Regulations. It is important to note that with a few exceptions, bands are generally allocated to more than one radio services. Constraints, so there are a few constraints. So here we have shown Earth atmosphere. So you can see we have the homosphere and heterosphere, right? So here we are actually moving away from the contour of the Earth, and here we have homosphere, and then after that we have the heterosphere. So now we will be talking about the atmospheric losses. So different type of atmospheric losses we can have that can actually disturb the satellite communication. So these losses are atmospheric absorption, then atmospheric attenuation, then traveling atmospheric disturbance. So here we have shown this is frequency and this is the total attenuation in dB. So you can see as we actually move on the frequency axis, right? So you can see that the attenuation is on the higher side. Gases which varies with the frequency of the radio waves, two absorption peaks are observed, right? So you can see for 90-degree elevation angle, right? And then for other elevation angles, that is 90. Okay. So here we have atmospheric attenuation, absorption after absorption, attenuation. So rain is one of the main cause of atmospheric attenuation. as opposed to ice and snow, because they have a little effect on attenuation because of their water content. From rain can be determined by A is equal to alpha LdB, where alpha is called the specific attenuation and can be calculated from specific attenuation coefficients in tabular form that can be found in a number of publications, right? And L over here is the effective path length of the signal through the rain. So the effective distance that the signal has to traverse through the rain. Okay. Then we have traveling ionospheric disturbance. So we have scintillations, polarization, rotations, right? So now what is polarization? Is the property of electromagnetic waves that describe the direction of transverse electric field, consist of an electric and magnetic field. So the electric and magnetic field, they are coupled, vibrating at right angle to each other. So they are at right angle to each other. So it's important to adopt a convention to determine the polarization of the signal. So normally the magnetic field is ignored and the plane of the electric field is used. So here we have different type of polarization. So you can see this is linear polarization, and then we have circular polarization and elliptical polarization. So linear and circular polarization. So you can see the effect of polarization when we talk about the satellite communication. So this is vertical linear polarization and this is horizontal linear polarization. Okay. So here we actually have mentioned different ways to categorize communication satellites. So one of the key factor is coverage area. We can categorize satellite communication on the basis of coverage area, global, region and national. Then we can also categorize satellites or satellite communication on the basis of services. They offer fixed service satellites, broadcast service satellites, and then mobile service satellite. And then we can also establish some of more categories on the basis of general usage: commercial, military, amateur and experimental. So here we have classify or you can say classification of satellites on the basis of the Earth, and this we have already discussed, right? So you can see circular, elliptical orbit around Earth in different planes, polar and other altitude of satellites, right? So minimum elevation angle. So this already we have gone through, right? So here is the table. So and here we have the performance factors regarding the satellite. Distance between Earth station antenna and satellite antenna. So this is one of the performance factor. Then for downlink, terrestrial distance between Earth station antenna and aim point of satellite. Atmospheric attenuation affected by oxygen, water, angle of elevation and high frequency. So these are the factors that we will take into account when we will be talking about the satellite link performance. So here configurations, so you can see point-to-point link, Earth station, and then this is the ground station. So broadcast, so here we have point to many point, and here we have discussed or shown capacity allocation strategies. So how we can enhance the bandwidth or the capacity of the satellite. So we can use different techniques. For example, we can use FDM, you can see division multiple access, FDMA, TDMA, time division multiple access, and then CDMA. Okay, so frequency division multiplexing. So of course we know that alternate use of channels in point-to-point configurations. Then frequency division multiple access, right? So factors that limit the number of subchannels provided within a satellite channel via FDMA: thermal noise, intermodulation noise, and crosstalk. So here we have different forms of FDMA: fixed assignment multiple access, FAMA, and then demand assignment multiple access, right? Then FAMA, FDMA. Logical links between stations are pre-assigned, and multiple stations access the satellite by using different frequency bands, and we use considerable bandwidth. We can have and then we have single channel DAMA, FDMA, single channel per carrier, and then set of subchannels in a channel is treated as a pool of available links. Right. So here we have mentioned the reasons for increasing use of TDM techniques, time division multiplexing. So the most important factor is the cost of digital components, right? Because it's dropping day by day, and then of course we have advantages of digital components, and those components, they favor us actually in case of errors, and we are on the safer side for error correction codes that are being used in order to correct the errors. Then the TDMA techniques, they provide higher efficiency, lack of intermodulation noise, so we can also avoid intermodulation noise. So here FAMA, TDMA operation, and here we have shown graphically FAMA and TDMA uplink. So you can see that we have station 1, station 2, and station 3, right? So you can see that the frame time, right? And here we have the transmission bus slot, and this is the bus sub slot, right? Okay, so here you can see we have the FAMA, TDMA downlink, same station 1, 2, 3. So transmission from station 1, and then right, transmission from station 2. So you can see 3 to 1 to 3, right? So we have transmission from station 1, right? Okay, so that's all for today's lecture. So today we talked about satellite communication, and we established that why we need satellite communication. And then as we know that when we talk about satellite communication, so we use one frequency for uplink and another frequency for downlink. Moreover, we use higher frequency for uplink and low frequency for downlink. So why we use, first we have to mention, or we have to justify why we use two different frequencies. So of course, in order to avoid interference, we use two different frequencies. So there are other factors which we have mentioned in order to justify that why we are using two different frequencies for uplink and downlink. And then we also justified that why uplink frequencies are on the higher side as opposed to the downlink frequencies that are on the lower side, or that are lower than the uplink frequency. Then we can classify satellites into different types on the basis of different characteristics. So we have mentioned different types of satellites. So the coverage area provided by the satellite is actually defined as the footprint. So we have defined the footprint of the satellite, and we use that footprint in order to define or explain different features of the satellite. And then satellite transmission is performed, or it support different frequency bands, or it allocate for satellite communication, different frequency bands are allocated. So we talked about different parameters, different characteristics, different metrics regarding those different transmission bands, the frequency range, the orbital distance, and the time period, right? So then we talked about the propagation delay, and one of the important element when we talk about the satellite communication is the transponder. So we talked about the design or the electronics that is involved in the transponder, and then of course we have some impairments that come across or that come that we have to face when we talk about when we have to establish the satellite communication, and effect of rain is one of the impairments that we have to face when we talk about the satellite communication. Then we justified why we are using microwave communication, and we have shown or mentioned a few points in order to justify for the selection of microwave frequencies in order to accomplish satellite communication. And then we can also enhance the capacity of the satellite. So what are different mechanisms, methodologies that are being used in order to enhance the satellite capacity. So that's all. आज के लिए इतना ही काफ़ी है. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम.